All right, go ahead.
All right, very good. Good to be with you again. We are in chapter 12, the second part of chapter 12, the oxidation part. Last time we did the reductions, and now come the oxidations. We're meant for Friday, March 27th, and also we'll be finishing chapter 12 today, so your homework 12 is due tonight. Make sure you upload that before midnight. And also chapter 13 coming up, mass spectrometry and IR. And make sure you read ahead on that one. It'll be a little bit different because now we're into structure determination using different analytical techniques really, but we'll show you how we determine the structure of different compounds. So if you look up on the chart here, the outline, that's what we did last time, the beginning part of chapter 12. We'll have a little bit of review at the end. We'll do some more reactions, but we have hydrogenations, both of alkenes and ketones and aldehydes to alcohols with palladium or platinum catalyst and hydrogen. Remember, it's a little easier to do the alkene reductions. We also did hydrogenations of alkynes. So if you have the active catalyst with hydrogen, you go all the way to the alkane. Now, if you have the poison or Lindlar catalyst, remember you can just say Lind, that's fine, as long as you specify that poison catalyst. You don't need to show all of the actual ingredients of that catalyst, the calcium carbonate, the lead acetate, quinoline, whatever. But that gives the cis alkene. We call that the half reduction, or the poison Lindlar reduction of alkynes to cis alkenes. Now, if you want the trans alkene, we can do that. It's using sodium metal. Remember, that's also a reducing agent because it has available electrons. There's a valence electron. This is sodium metal, the shiny stuff in ammonia gives us the trans alkene there. We also did LAH reduction of alkyl halides to alkanes and opening up of epoxides to alcohols with LAH. Remember what LAH stands for? Lithium aluminum hydride. Okay, now let's look at the oxidations we'll be doing. We already reviewed those last time by the introduction, so I'm not going to go through it step by step, but we have a few new reactions now, and here are the key reagents looking at here on the board. And a few of these are very important, a couple acronyms that are new we'll have to keep track of. Oxidizing reagents, you're probably familiar with peroxide if you ever bleached your hair or done the laundry where you got to get rid of a bad stain. This oxygen-oxygen bond here can undergo oxidation reactions. And what do you see here? Oxidation, you see a lot of oxygen, okay? Remember, that's the hallmark of organic chemistry oxidation. We're adding oxygen and or removing hydrogens. We can have acyl variations of peroxide. These are called peracids. This is peracetic acid. You see, if we just had a hydrogen right here on this oxygen, that would just be good old acetic acid, right? But we've got the two oxygens. It's a per-oxy compound now. This will be an important epoxidizing reagent. Now, this is the one that's always used. It's kind of a pain to work with. It's a liquid. We like MCPBA, metachloroperbenzoic acid. Don't worry about all the naming there. We haven't taught you how to name aromatic compounds yet. This is the meta position where that chloride is. And this acid here also does epoxidation. It's a nice, solid, convenient material. This one here is the magnesium salt of orthoperthalic acid, and it also has the peracid here. It has a salt form, this carboxylate salt, which makes it more polar and a little more convenient sometimes. This is MPP. You don't need to worry about that one. MCPBA will suffice on a quiz or a test, but make sure you know what the acronym is and know what the structure is for epoxidation. Now we'll also have alcohol oxidations to ketones and carboxylic acids. Chromium oxide is the standard one here. This is a carcinogenic material. It's a red material. We can form it in different ways. The active thing is actually the chromic acid, H2CrO4. This is not sulfuric acid, okay? This is chromic acid, the transition metal. So that will be the potent oxidizing agent. We can also have an attenuated oxidizing agent, which is called pyridinium chlorochromate, is what the PCC stands for. not the Polynesian Cultural Center. Okay, so we're not talking about Hawaii. Pyridinium, it's the salt form here, and it has that chloride out here, which attenuates their activity. This will take primary alcohols and stop the oxidation to aldehydes, whereas chromic acid will take primary alcohols all the way to carboxylic acids. Both of them can take secondary alcohols to ketones. And we'll have to look at the structure. Again, everything comes out of the structure. Another couple ones to keep in mind coming up, osmium tetroxide will be oxidizing alkenes, fudiols. Potassium permanganate can also do that. Ozone is a very aggressive oxidizing agent. It's a gas molecule. It's used to purify different things, including swimming pools and other things. It's a disinfectant reagent. But it will take alkenes to ketones and aldehydes. And then Mother Nature's oxidant is actually nicotinamide, adenine, dinucleotide, the positive cationic form. And this is how alcohols are taken to aldehydes and carboxylic acids in the cell. So we'll relate that to some of these here. But those are the oxidizing agents we need to know. Let's look at them and get into some of the specifics here. The first one we're going to look at is epoxidation. So we're going to be using the per acids and MCPA or peracetic acid, either one, will take an alkene to a epoxide. So yeah, you have to have the per acid. A normal carboxylic acid will not do this reaction. And what we get is the epoxide, okay? So an alkene to an epoxide. The pi bond goes away. We have two new bonds to oxygen, carbon, oxygen, so it's a very useful reaction. Let's look at some specific examples here. So let's see MCPA here with 1-butene, and that will go to the epoxide. And then we've got cyclic alkenes, same conditions here. We'll also go to the epoxide here. And a couple other things to look at here. Let's look at trans alkene, 2-butene, versus cis 2-butene here. What do we get? MCPA with this alkene, we're going to get trans epoxide. Okay? These two methyl groups will still be across from each other. And what do we get here from the cis? We get the cis epoxide. The two methyl groups are still across from each other. Now, what about stereochemistry? Are any of these stereocenters? This one right here is, and with MCPPA, we can either form the top or the bottom there. So that will be a mixture of what? Enantiomers. How about from this one, cyclohexene? No, there's symmetry in this molecule, so that's achiral. Don't need to worry about that one. What about from the trans one here? These two right here are also stereocenters. So that will be a DL pair. But notice the other enantiomer will also be the trans epoxide, the two methyl groups trans. What about if it's cis here? No, then we've got symmetry here. This one will be achiral. So we need to use this information to figure out something about the mechanism of the reaction. One thing to notice here is that tetrasubstitute alkenes, tetra, react very fast than tri, faster than di, faster than mono. So the more electron rich an alkene is, the faster it will react. That says something about the mechanism also, along with the stereochemistry. So let's look at the mechanism. And this kind of goes along with the structure of the alkenes, we can say. How do the electrons actually go in this reaction? Let's look at our alkene here. And whatever we've got on our alkene, this is what, sp2 hybridized, trigonal, planar. We've got our pi bond there designated. And now let's have our per acid up here. Our per acid will look like this. If it's peracetic acid, that's just a methyl group. If it's MCPPA, that's that benzene with a chlorine on it. And I've drawn it in this conformation. And this oxygen right here is going to undergo attack by the pi bond with loss of those electrons. Okay. So this is a relatively weak bond right here. And look, if we break that bond and push the electrons to this oxygen, we have resonance stabilization on the carboxylate. Okay. So the pi bond's coming out in that way. Now we can keep these electrons kind of coming around here, and that frees up this to come in and fill that position on the alkene there. So let's see, what's the result here? Well, we'll have this new carbon-oxygen bond here from the initial movement of the pi bond electrons, and then these electrons coming down from the hydrogen-oxygen bond to fill in that part there. So, and then what is the acid in this? Well, that gets the proton up there, and look, this becomes a carbonyl here. So you can see whatever stereochemistry was on the alkene is transferred directly into the epoxide. So you can see if we've got a cis alkene, for example, we've got two methyls here sticking out in the front. Those two methyls will still be cis to each other in the product, okay? We say that the reaction is stereospecific that way, and that cis goes to cis, okay? And the trans alkene will end up in the trans epoxide product because of this concerted mechanism that's known. This is Paul Bartlett at Harvard in the 1950s. You don't need to worry about that. But a lot of people wondered about this mechanism and how it would go. Now, you can do it stepwise. Let's do the whole mechanism here again, just stepwise. This concerted thing is kind of hard to keep track of all the electrons. Well, let's just keep track of it one step at a time. How about if we just stop at that point and see what we get? Well, we'll get O minus there, or carbonyl. And there you see that carboxylate resonance, right? And then here, what do you see? You see the OH will still be on there. And this, okay? I guess, yeah, that hydrogen is still on there, okay? That used to be on the per acid, right? And so what else do we need to do? Push these electrons over here, grab that proton there. These electrons will be liberated, and that can go down, you see, and then form the epoxide product. So the stepwise thing, you kind of see the electrons a little more localized, but this stereospecific effect comes out there. So the mechanism is different than what we've seen before, but it's not too bad that way. All right, let's go back to the overheads up here. We'll look at a couple things here, application-wise. So here's our oxidations that we're doing today. We just did epoxidation up here. We'll get to these other two here in a second. I wanted to jump a little bit ahead and show you this. So here's a compound called disparlure, and this is actually an insect pheromone from the gypsy moth. So a little chemical ecology here, biology overlap. This pheromone right here has this cis epoxide, and it has different alkyl chains here. So this is actually a chiral, an anti-impure molecule in nature, because these two chains are different here. But you see the cis relationship there. The two hydrogens across and the two alkyl chains are cis to each other. This could come from, what, an epoxidation reaction of this cis alkene. And this could come from an alkyne that we could do, what, the Lindlar half reduction. So these open arrows are the retrosynthesis, kind of planning the synthesis here. But you can kind of see how this molecule could go together. So it's a complicated synthesis problem. And at least with MCPPA or peracetic acid, you could take this cis alkene to the cis epoxide. And then how do we make this? Well, that's two alkylation reactions. If we could take acetylene gas, deprotonate with strong base, form the anion, and then alkylate here, and then another equivalent of base, and then put in another alkyl halide, bromide in this case, we could put that on. Now, there are versions of this that can go enantioselectively. and maybe we'll get to that at the end. We have some time, the sharpless epoxidation. So this is the forward direction, showing you just what we described there with the synthesis. And the key thing is this Lindlar catalyst. Remember, that's palladium with the poisoning, the calcium carbonate, the lead acetate, and the quinoline. You don't need to draw that, just say Lindlar is fine there, and let this alkyne can go to that cis-alkene. Let's see, is that sharpless thing there? Okay, yeah, MCPBA, it's showing you here, if you do this, MCPBA will form both enantiomers of this. This is the biologically active pheromone. This is the inactive enantiomer. Remember, the receptors for these pheromones and other biological molecules are proteins. They're also chiral, so you get that differentiation there. The chiral forms can have different activity with other chiral molecules, like the receptors for this. And maybe we'll do the sharpless thing later. Oh, here's another epoxide I want to show you. I forgot about this one. I may have mentioned this one before. Here's epoxy resins, and maybe you've used these before in the shop or doing repairs at home, whatever. It's a tube with two different materials, and the two different tubes have a diepoxide shown here, and the other tube has a diamine right here, and some base. And when these two come together, the amine opens up the epoxide, cross-links, and forms this covalent epoxy resin. Very durable material, very strong materials. They make all sorts of things, including car parts and other things. But here's how it's made. Here's how the epoxide is made industrially. It's made from this diphenol up here, and sodium hydride forms the anion there, takes the proton off. The O- then with the allyl bromide forms the allyl ether. And then MMPP is that magnesium salt form of the peracetic acid. You could say MCPBA also here would be no problem. And that will form what this epoxide. So this bisphenol A epoxy, and there are other bis epoxies that are known for different types of resins. This isn't the only one, but this is a very robust one that comes out of that process there. So anyway, epoxy resins are also epoxides. That's the same term there. Oh, and then the sharpless asymmetric one, we'll get back to that later. We'll say some more later on there. Let's first do dihydroxylation and the chromium alcohol oxidations to carboxylic acids and ketones. Let's first look at dihydroxylation. So we've got alkenes again, and we're going to take an alkene here, and we're going to react it with osmium tetroxide. Wow, 4 oxygens? We'll have to draw out the structure of that. And first of all, I'll have to point out in the periodic table, where is osmium? Let's see. Well, it's element 76 there. It's kind of in the middle of the D block, and it's down in the 4th row there. So this is a heavy metal, transition metal, and it's in a highly oxidized state. And again, that's another way to remember these oxidation reactions. If you see reagents with a lot of oxygen, think of the oxidation reactions. The specific one that this does here is form the diol product. So it takes an alkene and goes to the 1,2 diol. So they're on the same carbon there. Both carbons of the alkene, the pi bond's gone. And again, like the epoxide, 2 new carbon-oxygen bonds are formed there. Let's look at some specific examples. So if you take butene here, you get this diol. Okay. Very different product, right? This is a gas molecule. This is a liquid material, very polar. This one's water soluble, this one's not. Again, appreciate the difference in the properties of the compounds we're making here, why these reagents and reactions are important that way. Let's look at this one, maybe a cyclic one with an alkene on the side there. We do osmium tetroxide there. We can get this diol product. Okay. This one's kind of important to point out. If we take this cis one in a small ring like this, cyclohexene, and do osmium tetroxide, what do we get here? We get the 2 alcohols. Are they cis or are they trans to each other? Well, the determination of the stereochemistry says something about the mechanism here, just like we saw with epoxidation. It turns out they end up cis to each other. Okay, so the two alcohols are on the same face. They're not trans to each other. And notice what? This is achiral one, so you don't need to worry about stereochemistry there. We can do the same thing with the cis and trans two butenes. If we do the dihydroxylation here, what do we get? You see the two alcohols are on the same face. Okay. And if we do the cis one, what do we get here? They're also on the same face. And notice the stereochemistry is maintained here. Let's see. Comes down on the same face. You see the two alcohols are syn to each other here in the product. So is this one, let's see, that is the stereocenter. That's the stereocenter. Is this the chiral molecule? What would you say? Well, sign R and S here. You can do that. This is the R one, right? It's also formed along with the SS one. So indeed, this is what? A DL pair. This is a chiral one. So that's why that sharpless reaction is coming up here, the asymmetric epoxidation. There are asymmetric osmium tetroxide reactions that are not, we're not covering those. We're just showing you the one example of the asymmetric epoxidation. But you see this one, if you have the cis alkene, the two alcohols are both on the top. You see the stereochemistry maintained here. But we already are drawing what? The conformation where you can clearly see the mirror plane in the molecule. So that's indeed achiral. Okay. So our mechanism has to account for these observations. So let's see. How is this reaction going to go? Well, let's draw our alkene here. Let's stick with cyclohexene. I'm kind of drawing it edge on, so we're kind of tipping it up there, kind of flattening it out so we can see everything. These hydrogens are coming right out at you. Okay, there's cyclohexene. Then let's have osmium here, and let's draw out the structure. So it's osmium, and remember an oxide is a what? It's 2- ligand, if you remember your Gen Chem. So the oxidation state here of osmium in the tetroxide form, that's osmium what? In the +8 oxidation state. Now that's a formal oxidation state. We don't say the osmium has a +8 charge. That would be very unstable. But with the 4 -2 oxide ligands around it, we say it's in the formal +8 oxidation state. Okay, so how does the reaction work? Well, let's take our pi bond and attack, bring it down as a nucleophile, and push the electrons into osmium. Okay? So in effect, we're reducing the osmium from this unstable +8 oxidation state. This motion of the electrons down into osmium is what? Reducing it. And then let's take this pair of electrons and attack the other side of the pi bond. And this is kind of similar to the, what? The epoxidation reaction. It's concerted this way, and it maintains the stereochemistry. So let's see. We'd have what? We'd have the 2 oxygens here around the osmium, and the result will be that. This is called the osmate ester. It can be isolated in some cases, but notice here we've got the 2 hydrogens up and the 2 oxygens down there. And what about the oxidation state of osmium? This helps you keep track of things, by the way. Carbons have undergone an oxidation. The metal has undergone what? A reduction. So now it's not in the +8 oxidation state. It's in the +6 oxidation state. Okay? So you see it's got 1, 2, 3, 4, 5, 6 bonds to oxygen. -1 for each one on there. Now the next step here is just called hydrolysis, or using water to break up the osmate ester. There are ways we can push electrons to do that, transfer protons, whatever, and what we get to is the diol product. And osmium stays in the +6 oxidation state at that point. Okay. Now, there are ways to recycle the osmium-6. We can oxidize it back up with a compound called NMO, which stands for N-morpholino N-oxide. And maybe I'll show you that. It's a way to take it back up there. This material here, morpholin is that 6-membered ring with the oxygen and nitrogen. N-methyl is the N part, and then O is the oxide form. That will take osmium 6 back up to osmium 8. You can actually then use the osmium catalytically, which industrially, that's an important thing, because this is a toxic material. This will cause all sorts of problems if you're exposed to that. So we like to point out some green chemistry where there are some environmentally friendly reactions, and this one is certainly one now that can use the osmium catalytically there. Even though it's dangerous, as long as it's contained, it's not a problem. And you have excess of the NMO. For a quiz or a test, you don't need to write that. All you need to write for the reaction over the arrow is this osmium 4, okay? And then maybe in the presence of water. But if you leave out the water, we'll still give you a credit there. Osmium tetroxide with an alkene goes to the product there. Now you can also use KMNO4, which is a salt form, potassium permanganate. It's a different metal, but it's also highly oxidized. It will also form the diol reaction shown there. Although osmium's faster, better reagent for it. Now we get out this cis diol. What if we want the trans diol product? Let's put these two up here. And this forms kind of a complementary type of reaction here, right? So if we've got trans, we have a good way to make cis. How can we make the trans product when we want it? This is the achiral one, okay, at least in this case. This is the chiral one, okay. And if we want to make that, let's see, we can take this and with osmium, you see we'll just get the cis. So we can't do it with osmium. Is there another reaction we could do first? Well, let's do MCPBA. And remember what? We get the cis oxide. Okay, that's also achiral. But look, we've oxidized the 2 carbons. We have oxygen on there. And we have what? A reactive epoxide. What can we do the epoxide maybe to get the trans product? Think about that. How could we open up that epoxide? Any ideas? We could react it with what? How about sodium hydroxide? There's one of our good old SN2 charged nucleophiles, right? So what would that do? It would do a backside attack right here, pushing up the hydrogen that's in the back right there right now. And what? That would give us the ring open thing. OH would be on the bottom. O minus would be on the top. And how do we finish it off? Well, water would just neutralize that. Okay. So these 2 reactions, MCPBA with the SN2 opening up with hydroxide, is complementary, we say, to the osmium tetroxide reaction. Okay, both of them are stereospecific, giving this cis-type product, and that's because of the syn addition. MCPBA, the per acid right on the top. Same thing with osmium tetroxide. Well, I'm showing it from the bottom right here, top or bottom, because it's the same product, doesn't matter. But it's also syn addition, okay? The 2 oxygens, the osmium tetroxide come in from the same phase, just like MCPBA when it forms the epoxide from the same phase. But we can make it complementary in the stereochemistry by also using in conjunction with it the SN2 opening. Question on that? That's an important sequence of reactions there that point out those differences. All right, let's get into ozone. Now, ozone. We need to talk about that and maybe draw the structure of it. You've heard about ozone before. We've used it in general chemistry. We've had you draw the Lewis dot structure of it. And that's always a little bit of a tricky thing here. Let's make sure we can do that. What do we get here? So that one would be neutral. Let's see. Did I do that right? Maybe I need to verify. Yeah, Isaac says it's right, okay. So yeah, ozone here. It's not the same as oxygen, which is O2. That's the abundant molecule in the atmosphere. Luckily, ozone is not very abundant. On a smoggy day in Los Angeles, it can be quite abundant. That's different processes from the sunlight on different pollutant materials. But ozone here is made from an electric arc. So if you pass oxygen gas through an electric arc, and you can do this with an arc welder from the garage, whatever, if you've got one of those, you can form the ozone. We do it in the lab with a specialized instrument called an ozonator, where there's a stream of oxygen passed through the electric arc, and then an inert carrier gas will bring the ozone, the O3, into contact with whatever reagents we're using. But it's a very aggressive reagent. It does things to alkenes. So if you have ozone here, and whatever you have on the alkene, both pi bond and sigma bond are broken. And this is the only reagent where we've got that. You can think of this as molecular scissors, just chopping both the pi bond, which we've always been breaking, and the sigma bond. Okay? So ozone is going to do some different things here. Let's look at some specific examples. So if you have one butene here, you'll generate this aldehyde. Remember, there's a hydrogen right there. And this carbon here has, what, 2 hydrogens on it? So you'll generate this guy also. 2 carbonyl compounds. So the propanal, the aldehyde right here, and also, what's this one called? Formaldehyde, if you don't remember that one. Don't worry about naming aldehydes and ketones right now. We're just worried about the reactivity of it. But if you have the alkene right here, it's going to be different, right? It's going to be 2 molecules of acid aldehyde, okay? They'll be symmetric on both sides. We just have that. Let's do one where we've got some different stuff here. Oh, how about this one? A cyclic alkene with ozone. And we're going to form a ketone right there. And look, this part will link around here. The tether is not going to get broken. Just right here, break the pi bond and the sigma bond. We'll get, what, a methyl ketone up here. And count carbons. That's kind of an important thing to keep track of there. How about this alkene? So if we have that one on the end there, we do ozone. Look, we're going to end up with cyclohexanone and what? Another equivalent of formaldehyde. Okay. So let's come up with a mechanism for this and see what we need to do. If you just say ozone for that, that's fine. We also have dimethyl sulfide, which is added on there. So, and you should show that. It's really a workup material, dimethyl sulfide. If you leave it off, we'll still give you full credit, but it's actually a detonation hazard if you don't work up the ozonide, which we'll see from the mechanism why it's important to add the dimethyl sulfide. But let's do a little bit on the mechanism and see how this guy works. So the reaction involves, again, an electrophilic attack onto the alkene. So let's redraw ozone here. I'm not going to draw all the electrons again, but there's the thing. You see this oxygen right here has a plus charge. That makes this bond what? Electrophilic, right? So let's bring the pi bond over here and push the electrons there. Okay. Now we're kind of, the theme today is these concerted mechanisms, right? If we bring out these pi electrons here, we could draw an intermediate where we have what? A carbocation right there. But let's not let that sit around. Let's just add that. And what do we get? We get this 5-membered ring called the ozonide. The ozonide is a dangerous material. It's a trioxide. These oxygen-oxygen bonds are very weak. It's actually a detonation hazard. It can actually explode under certain conditions. So the next thing is actually breaking up that material. And it will actually decompose on its own in this process shown here, where we break the sigma bond. Notice we've already broken the pi bond in that first step. But if we use this pair of electrons to come over here and then break one of the oxygen-oxygen bonds here on the side, notice we'll get this intermediate here, where we have one side will be a carbonyl already. One side over here will be what's called a carbonyl oxide. And we don't need to worry about that, but this can actually flip over to give this arrangement, and then this can actually snap back shut to go from one ozonide to this other one, which looks like this. Now they're both 5-membered rings. This one has the 3 oxygens together. That's called the primary ozonide. This is called the secondary ozonide, where now the oxygens are not all right next to each other, but you still have this weak oxygen-oxygen bond right here. Now, that will just sit there in the flask after you've treated your alkene with ozone. What you need to do is to add the dimethyl sulfide. And this dimethyl sulfide has an odor associated with it. This kind of lets you know you've got it in there and it's doing its thing. It will undergo an oxidation reaction and it will break open the ozonide and form your carbonyl compounds very successfully. So let's see how the mechanism goes here. We can attack that oxygen and break this bond here. Let's go to that point. So we have O- here. We have O sulfide here. And notice when we push the electrons from the sulfur lone pair into this oxygen and break that bond, we have O- and we have also sulfur, cation, a sulfonium ion it's called. Now, how do we get to the carbonyls? Well, it's actually just one step. Take this pair of electrons here, break this bond here, and break that bond there. There's our first carbonyl compound. Whatever was on the alkene is now on that oxygen, and it's an aldehyde or a ketone now. And then this one here is that one, which we just got out of that position. And what happens to the dimethyl sulfide? It's now DMSO, dimethyl sulfoxide. You've probably heard of DMSO as a solvent, whatever. It is the byproduct of this reaction. Notice the sulfur gets oxidized, and the ozonide, you could say, got reduced. We pulled out 1 oxygen because 3 oxygens went in from the osmium reaction. Now, this part of breaking down the ozonide, I've never put that on a quiz or a test, so you're off the hook. Yay, you can cheer at home and say you don't need to worry about it. But it shows you why this reagent is important and mechanistically how we get from the alkene to the carbonyl compounds. Okay? So whatever carbonyl compound you've got, you just break both the pi bond and the sigma bond, and it directly forms there. Let's look at a couple more examples of this. Sorry to keep going back and forth on you.
All good.
Okay. A couple more examples. This very versatile reaction. If we've got pentene with ozone. And let's be good here. Let's show the dimethyl sulfide workup. And we don't put it in at the beginning. It's a second operation in the flask. And what do we get out? We get out this dialdehyde. You don't need to draw in the hydrogens there, but make sure you count up carbons. You should have 5 carbons there in that dialdehyde. So that's kind of similar. How about this one? This is limonene. So here's limonene. We're going to do the oxidation. And we've got 2 alkenes here. So yeah, just conceptually break those 2 apart. And then let's draw the 2 products. So we're going to have a ketone up there. All the other carbon-carbon single bonds will stay intact. And we'll have another methyl ketone down here. And what happened to this carbon up there? Well, it's now formaldehyde. And what about this one? Well, this framework comes over here, and we have what? An aldehyde right there. So there's our product. It's a, what, diketone aldehyde and an equivalent of formaldehyde. So these things can get quite complicated, but you just keep breaking them up. One other ozone reaction, what if we have an alkyne? Well, we can do the same thing with ozone here, react it twice, and mechanistically it's kind of complicated. You actually draw two ozonides here with excess ozone, and eventually the diozonide breaks down, but instead of giving an aldehyde or a ketone, when we break an alkyne, it actually becomes a carboxylic acid right there, okay? So there'd be one 4-carbon carboxylic acid and then one 3-carbon carboxylic acid right there. So you give two different products. And I'm not going to go through the rest of the mechanism of that. It's a slower reaction, but osmium ozone will react here to form the cleaved products there, but now they're carboxylic acid. Okay, one more reaction to cover. Should take us about. So we just covered what? Ozonolysis. We did dihydroxylation, epoxidation. Our last thing is alcohol oxidation. And the key thing on alcohol oxidations here is we go from an alcohol to a carbonyl. So let's see, what type of carbonyl is it going to be? So with primary alcohols, we have the carbon just with one other carbon on it. So this is an alcohol on the end of a chain. And when we do the oxidation here, we're going to get the aldehyde. And if we keep oxidizing, we're going to get the carboxylic acid. So there's two different products we can get. Notice if we're on the end here, there's two hydrogens we can remove, right? Remember, oxidation means removing hydrogens. So here we added another bond to oxygen and removed a hydrogen. And here what we removed another hydrogen and then added another oxygen. Okay, so we've got this capability here. With PCC, we're going to stop at the aldehyde, but with chromic acid, we're going to go all the way to the carboxylic acid from primary alcohols. Okay. Then we have a secondary alcohol. This is different now. This carbon here that has the OH has two different carbons on it, and when it goes in oxidation, either one, either PCC or chromic acid, it will stop at the ketone. Okay? So again, we're forming a lot of different functional groups here. Now, to make the story complete, what about tertiary alcohols? So we've got an OH group on a carbon with 3 carbons bonded to it. We call that tertiary alcohol. Can that undergo an oxidation? Well, are there any hydrogens to remove here? It turns out that's part of the mechanism. There aren't any. Notice with secondary, we have 1 hydrogen we can remove to oxidize the ketone. Primary alcohol, we have 2 hydrogens to remove to go either to the aldehyde or all the way to the acid. So here, we get no reaction. So if you see a tertiary alcohol with either chromic acid or PCC, those oxidizing conditions will give no reaction there. So it's a little bit different here. So let's look at the different type of reagents that we have. We're going to have chromic acid and PCC. But we've got to examine the structure of our starting material, the substrate, in order to keep this straight. So we can make the reagent from chromium trioxide. That's chromium in what oxidation state? That's also a transition metal. It's in group 6 there. It can go up to an oxidation state of +6, and that's what it is here with the 3 oxide ligands on it. In the presence of sulfuric acid, H2SO4, and again, this is sulfuric acid, the stuff you know before, that is a sulfur there. This reaction here will make chromic acid. And I know that gets kind of confusing. Where's the CR? Where's the S? Whatever. This is the oxidizing agent, okay? This is not. Sulfur's not redox active here. It's in the higher oxidation state. But these transition metals, like we saw with osmium and permanganate, have the ability to transfer those oxygens. So this is the active oxidizing agent. chromic acid. You can also make that from the dichromate, which is a little bit cheaper material. This is sodium dichromate, and you treat that with the same thing, with sulfuric acid, and you can also make the chromic acid, which will do the oxidation. So let's see here. If you have 1 butanol, and you react it with H2CrO4, or over the arrow we might show sodium dichromate and sulfuric acid, or it might be chromium oxide sulfuric acid. Sorry, you see a lot of combinations for this. Or I like to just stick with chromic acid. This is difficult material to deal with. It's very corrosive, very toxic. So normally we just form it from the salt and then put in the strong acid. So it's kind of a practical issue here for why we have all these different forms. But chromic acid, H2CrO4, not S there. If you have sulfuric acid, it won't do the same thing. And this is what? A primary alcohol. So what's our product here? It's going to be the carboxylic acid. The alcohol gets oxidized all the way to that point. Now, if the alcohol's moved over one position, it's a secondary alcohol. What do we get here now? Not the carboxylic acid, we get out the ketone. Okay? So, similar type of thing here. Let's look at a little bit of the mechanism. Not too much though. So if we have this and we have chromium, it doesn't matter which one, and we're going to push electrons and transfer protons. I don't like to show the whole thing of this mechanism, except the intermediate here, which in the presence of water and the sulfuric acid, you get to this point, which is called a chromate ester. It kind of looks like an ester with another carbonyl, not on oxygen, but on the chromium. And the oxygen lone pairs, you see, attacked the chromium and made that intermediate. Well, then what occurs here? Well, you have this. A weak base here, water, can take the proton off there, flow the electrons up here to form the carbonyl, and flow the electrons into chromium. And chromium gets reduced, okay? Just like we saw with osmium. What do we get here? We get the oxidation product, in this case the ketone from the secondary alcohol. And the chromium winds up as the, not the chromium 6 oxidation state, but 5. And this can actually get protonated here and go to the 4 oxidation state. The +6 oxidation state has a red color associated with it. It's very distinct. The more reduced forms of chromium actually have green and blue colors. And this is the basis of the so-called breathalyzer test that law enforcement used to use for DUI suspects, where they'd have a little tube called the breathalyzer, and they'd make the suspect breathe into this tube. The tube initially was red with impregnated chromium oxide in there, a little bit of an acid, and there's some sort of an inert solid support material. As the vapors from the guy's breath passes through there, what are they looking for? They're looking for blood alcohol, ethanol, which is also in the breath. And so if they see the red color from the chromium go to green-blue, they know what? That the ethanol is being oxidized to acetaldehyde, and because this is a primary alcohol, onto the carboxylic acid. Now you don't see those, these are colorless, but what they'd see in the breathalyzer tube, and it's not a very accurate test, there's much more improved methods for determining blood alcohol content. But the degree of the color change can be correlated with how much alcohol from the breath is actually in the blood. So it is a reliable test for law enforcement to test that. But the intermediates is chromate ester, and then you see the reduction of the chromium going to a lower oxidation state as what? The substrate got oxidized. That's all you need to know in that mechanism. And I've never put that one on a quiz or a test either, but I think it's an important one to do. Now, let's say we want to, instead of go to the carboxylic acid here, we want to go to this. which is what? Only partially oxidized. You see that okay? I guess okay.
Yeah.
Yeah, okay, so the aldehyde here is on the end, and we just take off one hydrogen here. Remember, there's two on a primary alcohol. That's the key thing here. But you see with chromic acid, the strong oxidizing agent, we go all the way to the acid. But what if we want to stop at the aldehyde? The partial oxidation. So this is kind of like the Linlar partial reduction. This is the partial, what, oxidation. What's the reagent that does that? PCC, Polynesian Cultural Center. No, sorry. Pyridinium chlorochromate, okay? It has a chloride group on the chromium, and chlorine was electronegative, right? It's pulling electron density out of the chromium. It's still a chromate here, but it doesn't have any strong acid. There's no proton here and no water in here. It's also anhydrous, that's part of it. And it has the pyridinium salt, which is just the protonated form of pyridine. So that's the pyridinium chlorochromate, PCC, under these anhydrous, less reactive conditions with the electronegative chloride, attenuating the reactivity of the chromium, no water, stops at the aldehyde. Now mechanistically, there's ways to interpret that. The chromate ester can only form from this point, and you can't form the next chromate ester to do the extra oxidation here. That's a more advanced topic. I'm not going to show you that. All you need for the purposes of our exams is if you have a primary alcohol, you want to go to the aldehyde, just drop PCC over the arrow, and you'll be good, okay? So you can look at a couple others here. You could think of this alcohol, which is again primary. You say PCC, what are you going to get here? This primary alcohol is going to stop at the aldehyde, okay? And that would be your product, okay? Questions on that? All right, let's look at Mother Nature's oxidizing agent. Speaking of ethanol here, ethanol in the breath, the breathalyzer, let's tie that in with what happens to ethanol in the body. That's a good thing to be aware of, at least. And this is kind of looking forward to biochemistry and maybe wondering about some of these reactions in biology. So if you have ethanol in the body, the first step here is oxidation to the aldehyde, and then eventually in the liver it gets oxidized to acetic acid. Now, why would it want to go to the acid from the alcohol? Well, the alcohol is freely water soluble, that is true. The first oxidation product, acetaldehyde, is very electrophilic actually. This will actually cross-link with different primary amines, including amines on DNA. If this cross-links with some of the amines and the proteins involved in neurotransmission, for example, in the neurons, this can lead to the drunkenness effect. So it impairs the neurological transmissions there. You lose motor muscle control, slurred speech, whatever, thought control. And this guy, because it's electrophilic, is a big problem. Once it gets oxidized in the liver to the acetic acid, it's not so bad. High levels of acetic acid can be toxic, but it's even more water soluble than the initial alcohol. This is the bad actor. This is the one that can react with things. And it's made from this alcohol dehydrogenase. It's an enzyme, okay? And a key cofactor here is NAD+, okay? So let's look at just the basics of this. This is the cofactor, which is another covalent molecule, which is bound to this big enzyme, which has hundreds of amino acids. It converts ethanol into what? Acetaldehyde, which is an oxidation reaction. But there's no PCC here. There's no chromic acid, okay? Those reagents would be toxic to a cell. But NAD and dehydrogenase does this. So let's look at the thing here. So here we've got ethanol. And I'm going to draw out these two hydrogens here, and I'm going to draw out the cofactor, at least part of it, which is going to be the NAD+ part. Oh, so here's NAD for nicotinamide, which is actually this molecule right here. Pyridine with this amide, that's nicotinamide. Yes, it is related to nicotine, that herb from tobacco. Adenine, which is down here, which is like adenosine. You've heard of adenosine triphosphate. NAD for the dinucleotide. And then the plus. What's this plus mean? Well, if I draw this structure right here, is there some atom that has a positive charge? Yes, it is. It's right here. Okay. So the N plus is part of the structure right there for NAD plus. This is bound not covalently to the enzyme. So this big enzyme here is binding both that and the substrate, the alcohol. So how does this work? Well, let's see. Also in this enzyme, which is very big, there's an amine. Usually it's a surface lysine. Sometimes it's a histidine base, but it's a specific base that's found within the enzyme. Let's go ahead and grab a proton there. That will free up this pair of electrons. That pair of electrons can come in here and form the aldehyde. But notice we've got to pull out this hydrogen with a pair of electrons. Where's that going to go? We're losing hydrogen and this pair of electrons. That is an oxidation, right? So we're taking away hydrogens and electrons here. Where are those electrons going to go? Oh, right in here at that position on the pyridine. Push the electrons over here and push those electrons down here. Okay? Let's see the result of that movement of electrons. Kind of a neat reaction, I think. This combines the topic with biochemistry. So here's our nitrogen, our nicotinamide, and we've got an extra hydrogen right now. And we've got an aldehyde up here. So we already had a hydrogen here. This hydrogen, though, with its pair of electrons, just went on to the pyridinium, a pair of electrons. And what? We pushed these electrons down, and now this nitrogen, what? Has a lone pair on it. And now it's not positively charged anymore, right? Where'd the positive charge go? Well, it's out here on the enzyme. Okay? If we put a proton on that specific base there, it will be an ammonium cation. But there's a substrate. We've undergone the oxidation. Okay, and indeed that is an oxidation. And what happened to the NAD+? It's no longer NAD+, it's NADH. You've probably seen that cofactor also. This is Mother Nature's reducing agent with this H here. Because in theory, the mechanism is completely reversible, okay, which is kind of cool. Depending on equilibrium and the needs of the cell, if you have too much ethanol, it will undergo the oxidation and make this bad actor acetaldehyde. And that's probably all I need to talk about here. But you got the basics of it. All right, let's look at the sharpless asymmetric epoxidation briefly here. We got to go back to the overheads briefly. We talked about disparlure, this pheromone from the gypsy moth. There it is right there. We talked about the synthetic planning in the forward direction there, the SM2 stuff. You can review that. But notice with MCPPA here, we get both enantiomers here. Well, what we'd like to be able to do is to take an alkene and epoxidize with high enantioselectivity, one chiral epoxide over another. This reaction here is called the sharpless asymmetric epoxidation for Barry Sharpless. He did the work at MIT years ago now, and it turns out that these allylic alcohol alkenes are the ones that are very good for his catalyst system, which is these tartrate, these ethyl ester tartrates. Tartrates have two stereocenters. If you use the lever rotatory one here with titanium, you don't need to worry about all this other stuff. You get high enantiomeric excess. 95% is this enantiomer here, shown here. If you use the opposite chiral catalyst here, you get out the opposite enantiomeric product with also very high enantiomeric excess. So you can make either one. Now, for the purpose of a quiz or a test, if you want to make a chiral enantiopure epoxide, just say one or the other. Just say DET, titanium, and look, the co-oxidant here is a peroxide, terbutyl hydrogen peroxide. Don't worry about all the other conditions. Just put something down there. Or just say sharpless epoxidation. We'll let you off the hook there. and you can show either enantiomer. And don't keep track of whether lever rotatory goes to this form or dexter rotatory goes to that form. Just pick one or the other. It's understood how it actually works here. It's actually a bismetallic complex with the tartrates there. These esters are for the ethyl esters coming off here. It creates a chiral environment, and so when the peroxide here delivers to the coordinated epoxide, which is in pink here, it delivers it from just one face selectively, which is kind of cool. So this mimics nature's enzymes that do different asymmetric reactions with high enantioselectivity selectivity, but we know a number of these chiral catalysts that do similar things here. So that's all you need to know about that. Here's another couple of substrates. This allylic alcohol. The alcohol helps coordinate the titanium to do this, but you see with DET, the tartrate that's dextrorotatory, you get out this enantiomeric form of the epoxide. If you wanted this one, which is the minor one in this case, you'd switch over to the L form. And same thing with that substrate, very high enantioselectivity. Okay, yeah, and this is the rest of the story about that. Again, you don't need to remember which face comes from which tartrate for the sharpless, but show that there. So this was used to make the enantiomeric form of the gypsy moth pheromone there. I'm showing the actual allylic alcohol substrate. This was done by Bryant Rossiter, who got his undergraduate degree here at BYU, got his PhD at MIT, and did this work with Barry Sharpless years ago. But here's the tartrate, the one here, 94% EE. A couple more steps here to put on the other chain there, but the epoxide is enantiopure there. And that's the one that makes gypsy moths come from miles around attracted by that pheromone, which is kind of a cool thing. All right, now we got a couple minutes. Let's do a quick review of all these reactions and see how good you're doing. Let's go back to the chalkboard. We draw up a bunch of these reactions, and as a class, we'll kind of go through them, kind of review them here. Let's do this reaction. And once I get them up here, you can pause this and see how you're doing on the reactions. Just supply the product. Let's do some alkyne ones also. So excess hydrogen in this case, and just regular palladium. But let's also do the one here that's palladium Lindlar. Okay, with hydrogen. And let's do the one that's with sodium metal and ammonia. Okay, so there's 3 reactions coming from this one here. And let's do this alkene, MCPBA. And let's do an osmium reaction with this one. Oops. Osmium tetroxide, sorry. Let's also do this one with ozone. And let's do a couple of chromium reactions. How about this one with chromic acid? And let's do this one with PCC. And let's do this one with PCC. Okay, so you can pause it there if you want to do this real quick and go through it and see how you're doing on these chapter 12 reactions. And then unpause it, and we'll go through it briefly here as a class. So what do you get for this one? Alkene hydrogenation. Very good, alkane. Well, that's all you need to put down there. If you have the alkene, this is a tetrasubstitute alkene, hydrogenation with palladium. What do we get here? Now here, the stereochemistry is important, right? So what's this going to be? Both of these are going to be up, or both of them are going to be down, because the 2 hydrogens come in syn together, the same phase. So you need to draw the stereochemistry in that case, with both of them what cis to each other. Okay. See which one's next here. Oh, we have acetylene. Acetylene excess palladium. Yep. So it'll just form the alkene there. Cross there. 1, 2, 3, 4, 5, 6 carbons. Make sure you got that. Lindlar one. We'll have the cis double bond there from that one. And what about if we take the alkyne with sodium ammonia? That's right, the trans one. So we'll have the trans product. Notice that's different than the one from the Linmar reduction where we did the cis. Here we've got what? The trans product. Okay, they're complementary. Seen a lot of complementary relationships here. MCPBA with this cis alkene will form this cis epoxide. So, yeah, we'll still see the methyl and the ethyl there cis to each other on the epoxide. And that is a DL pair, okay? This is not an allylic alcohol. The sharpless epoxidation won't work well there. I didn't have one for that, but you can review that reaction. Then we got this one with the osmium tetroxide. So the cyclopentene with that methyl group there. Both alcohols from the osmium will both be cis to each other, okay? Methyl group down, or both down. Either way you want to draw it. Again, that's the DL pair. You draw the enantiomer of that. Both can come from the bottom or the top. That creates what? Stereocenters here. So that would be a DL. Ozonolysis, O3 with this. What's that going to give? Sorry, we're kind of running out of room here. Methyl ketone there, and what? Aldehyde right there. Okay. So again, that ozone breaks both the pi bond and cis bond. Let's see. Primary alcohol. That's the key thing to look at first for alcohol oxidation. And this is indeed an alcohol oxidation. It's got the chromium there. So what are we going to get? We're going to get the carboxylic acid. Okay? And that's not going to be able to stop, even if we could limit the amount of reagents. Okay, so you see chromic acid or chromium oxide, sulfuric acid, or sodium dichromate and sulfuric acid goes to carboxylic acid. PCC can stop at the aldehyde point. Okay. If it's secondary, we could use either one, PCC or chromic acid. And what will it stop at? Well, it can't go any further, right? Because it's from a secondary alcohol. There's only one hydrogen on there to take off. Okay. So both of them just go to the ketone product. And I think that's it. I think that reviews all the reactions, and very good. We're finished with chapter 12. Make sure you get your homework in by midnight tonight, and we'll help you out by zooming in office hours and recitations. Remember, Wallace and Austin both have their Zoom recitations going as well. And we'll see you next time. Thank you.